Good morning. We are continuing on the sixth of equations of motion. If you recall, we derived these equations of motion, and here this force component, total force here, which is the x component. What is this x? X is that body axis x, right? And we need to know what are those forces. This is aerodynamic force. This will come because of drag, because of lift. Ftx, these are because of propulsion, the thrust. And then Gx means the component of the weight or the gravity force. Okay. Similarly, along y, along z. Now the question comes, how do I define the orientation of the airplane? Because I cannot use body fixed axis system, because as the body rotates, body axis also rotates. So what is the way to define? There we try to define the orientation of the body with respect to inertial frame. Okay? Orientation of the body with respect to inertial frame. We define Euler angle or Euler angles, which are psi, theta, and phi. Please note that when you define Euler angle to locate a body in free space, the order is very important. The order should be in terms of psi, theta, and phi. That is extremely important. So for this part of the lecture, this course, you take it, the statement, you take it as a statement. I am not going to go deep detail into it. All these details we may be talking about in our next course, maybe a 10 hours course on advanced dynamic stability. Already we have covered so many things, we have to cover so many things. But remember, this Euler angles has to be in a particular order. Then how do I define psi, theta, and phi? Let us understand that. Psi means, remember, this is the airplane. Let's say this is the airplane. And let's say this is x, earth, as well as x of the body. I've aligned like this. And this is the y. And then z is into the board. Psi means, first rotation is psi means psi positive is right wing going like this. So this is the psi rotation. Okay? This is psi. Psi rotation means what is happening now, as I rotate by like this wing also comes like this, and this becomes your new y1 direction. Correct? Body fixed. Remember, this is like this, now it becomes like this. If I make it little bit of more exhaustive for your understanding. So this is the second orientation. What this orientation is after giving psi rotation. Okay. So now what has happened? The y has become y1 because it's a body fixed axis. Now what is theta? Theta is rotation about y1 axis. Correct? So psi, then now theta is rotation about y1 axis. And once that y1 axis rotation is given, now phi will be rotation about this x-axis, which is body fixed x-axis. So phi will be rotation about xb axis. Is this part clear? Let me demonstrate this. So let us understand physically what are the Euler angle. Assume that this is the airplane, and this is the x-axis of the airplane, and this is the z of the inertial frame. So I rotate it by psi. The moment I do it by psi, the y-axis becomes like this. So theta is what? Theta is rotation about this axis, theta. Okay. Now this is the x-axis, x-body axis. So what is phi? Phi is about this axis. Clear? I repeat again. This is rotation about theta. This is rotation about z-axis. So this is your new y-axis. Rotation about y-axis is theta, and this is the new x-axis, body axis. Rotation about x is phi. Okay. So this is the order of psi, theta, phi, and you need to understand that psi, theta, phi psi, theta, phi are not orthogonal. Okay. This is extremely important because you have seen that rotations are like this. Why this? Why do you need psi, theta, phi? Because I need to find the orientation of this airplane so that I can get the angle of attack, etc., etc. Okay, orientation is important, right? And if I want to get the forces, I need to know what is the orientation so that I can get the component of forces. We need to know the orientation of the airplane because we want to find out the forces along the local body fixed axis system. Okay? Let's say, for example, if I want to find out what is the component of gravity force along local body xb, and you know this is theta, and this is nothing but mg, then I can write fx is equal to mg minus sine theta. Similarly, you could see that for a given configuration where there is a bank angle, I would expect that you derive this yourself, and fz equal to mg cos theta cos phi. Okay? Please do yourself by giving appropriate rotation, and by now you know if phi is 0, this Fi goes. There is no Fi. Naturally, there won't be any Fi, but phi is 0, then there is a Fz. And of course, Fx doesn't depend upon bank angle phi. Okay? I need to add this explanation to you so that you understand what is the final form. Do not forget, we are developing these equations of motion for stability analysis. Okay? There is another word of caution. Please remember, this psi is called azimuth angle, and not yaw angle, strictly speaking, right? Because the psi is azimuth angle, not yaw angle, because yaw angle, when you talk about yaw angle, it is actually rotation about ZB axis. But what about azimuth angle? It rotation about the Z Earth inertial frame axis. Okay? These are some subtle things you should understand. And also, theta, Eulerian theta is called elevation angle. But not pitch angle, When I am talking about Eulerian psi theta, theta is elevation angle. Why? What is pitch angle? Pitch angle is the rotation about body YB. But what is theta? Theta you have seen, it is rotation about Y1 axis. That is, the plane was like this. After this, when I give a psi rotation, then the plane Y1 is this, and theta is rotation about Y1 axis. That is, Euler theta is rotation about Y1 axis. But when you talk about pitch angle, it is the final, whatever the orientation is there, YB axis, about that is the theta. So these are something very loosely used, and people often commit mistake, but I thought I will tell you, although we are not going deep into this part of understanding, this is just a warm-up so that you can take up the next advanced dynamic stability, which will be 10 hours course, where we will go one by one into all these things. It's also important to know what is angle of attack. Just for revision, alpha was tan inverse, W by U, and you can make out the vertical and the horizontal. And then beta we will be using as sine inverse lateral versus total velocity, which mostly you will find it is for small angle, it is like this. Okay. To complete this Sixdorf equation of motion, we need this navigation equation also, which is phi dot minus psi dot sine theta. Q is equal to theta dot cos phi plus psi dot cos theta sine phi, and R equal to psi dot cos theta cos phi minus theta dot sine phi. To complete the whole equations of motion, we also need to develop relationship between P phi dot R Q and etc. And the equations are like this. I am not deriving this, but we'll make a physical interpretation of this. What are PQR? PQR are the component of angular velocity of the airplane or the frame fixed to the body resolved along local x, y, z direction. I repeat again, PQR are the component of angular velocity of the rotating frame, which was with respect to inertial frame, right? They are resolved along local x, y, z direction or xb, yb, zb direction. And this you can derive. I need little bit of more of mathematics, rotation of axis system, then you can easily find this relationship. You can refer any book. Anyway, in our next course, we will be only talking about these things. I am just skipping all this derivation because our aim will be only to focus on the dynamic stability part. We will be mostly dealing with u dot, v dot, w dot, p dot, q dot, r dot equation. And among that, in this course, we will be mostly doing longitudinal equations of motion, which is perturbed equation of motion. As you recall, what we decided, we will develop equations of motion and introduce perturbation, and you will see that how the perturbed quantities are varying. Okay? If they are coming back to 0, we will say this is dynamically stable. Okay? So that sort of an approach we will be doing. We will play around this equation to develop field. Let us see m u dot minus Vr plus Wq equal to minus mg sine theta plus Fax plus Ftx. Right? Let us try to see what does this mean when you talk about steady state equation of motion. If I am talking about steady state, then what will happen? This will end up in u dot will become 0. So minus V1 R1. Whenever we will be writing 1, that corresponds to steady state, right? Place W1, Q1 is equal to minus mg sine theta 1 plus Fa x1 plus Ft x1. Okay. Similarly, I can write for other equation. If I see it here, okay. For example, if it is a cruise flight, let's say cruise flight. What will happen during cruise? What is the value of V1 or R1? There is no lateral speed, there are no yaw rate. So this goes to 0, this goes to 0. There are no Q1, there is no pitch rate. So what we will get? We will get 0 is equal to minus mg sine theta 1 plus Fax1 plus Ftx1. Now you see here, if theta 1 is 0, which is essentially true for a cruise, right? Then what do we get? We get Fax1 plus Ftx1 equal to 0. And that is nothing but minus d plus t equal to 0, and you know this is nothing but t equal to d. So you could see that from this equation I can get the simplified equations which you have been already using in a performance course. Similarly, you could see for other equations, and we'll try to do it another. Let us see what does this help. Now here, if theta 1 is not 0, what is that we are getting? Let us see this. Suppose if theta 1 is not equal to 0, then what happens here? This is 0 equal to minus mg sine theta 1 plus Fax1 plus Ftx1. Okay? So now I write this as mg sine theta 1 is equal to minus d plus t, that is the thrust, and then I can write v sine theta 1 is equal to minus dv plus tv by W. So this is Tv minus dA by W. So what is this? This is again giving us the old equation, the rate of climb. Okay, rate of climb versus excess power. So you are getting from all those series of equation by simplifying it. Like that, you can go on checking that. I thought I will mention these things before I go for dynamic stability analysis. Okay. Now take another equation and try to develop the field. Let us see the other equation, that is F ZA plus F ZT minus mg cos theta cos phi minus plus actually will be equal to m W dot plus PV minus QU. Now see here, if I put theta equal to 0 and phi equal to 0, theta equal to 0 and phi equal to 0. To be more precise, I should use the notation 1, steady state, right? Okay, all should be 1. Then what will happen? That will happen F ZA plus F ZT plus mg equal to 0. Okay, what is the value of FZT? FZT means component of thrust along z direction is 0. So then we have FZA equal to minus mg, and FZA is nothing but minus lift as far as direction is concerned. So you get a relationship lift equal to mg, lift equal to weight. So again you are getting the popular equation from the series of equations of motion, lift equal to weight. Okay. So this is the way I thought I'll give you some examples so that you understand correctly, get some feel. This part of the lecture was almost like a discussion, and just to prepare you for dynamic stability analysis. Do not forget what the approach would be like. For example, when I am introducing perturbation, we are talking about small perturbation. You will see soon we will be talking about all those things. Talk about small perturbation. The understanding is that I can linearly add the perturbed velocity or perturbed quantity to the steady state quantity to get the total quantity. So U total after perturbation is U1 plus small u. So this linearity is allowed. Also, V I can write as V1 plus small v, W equal to W1 plus small w. So what are the U1, V1, W1? They are the quantities at the steady state. For example, if cruise is our equilibrium point, then the value of U1, V1, W1 is at cruise flight. Okay. And then P, I will write as P1 plus small p, Q as Q1 plus small q, like this, R equal to R1 plus small r. And we should also note down one thing, since we are talking about small perturbation, that means the product of two perturbed quantities will be negligible enough to be neglected from the analysis. This assumption also we will have. Okay. This is one. And then second thing you should also understand, when we talk about aerodynamic force, let's say Fxa, I will write it as Fxa1 at steady state plus small fx. Similarly, for Fz, it is small fz. Right? And what is this Fx? Fx is the perturbed aerodynamic force. Okay? And this we will see that Fx will be function of alpha, perturbed pitch rate, perturbed delta E, like that, And that again will be, you see how beautifully you are using the same concept of Taylor series and linearity and try to get those derivatives and completely estimate or model the functionality of perturbed aerodynamic forces in terms of perturbed motion variables. Okay? And then you will see how do you handle, get the characteristic equation and get the roots, and the roots are negative, then we have a different meaning, roots are positive, have a different meaning, and that is how we will be analyzing the dynamic stability of an airplane. Okay? Thank you very much.